Welcome back to ECE 320A. We only have 3 class meetings left. So we have half of the semester to cover in the next 3 lectures. Not quite, but that's what I feel like. We will cover Bode plots today, and homework 9 will open up right when class ends, and you'll be able to hopefully work through that a little quicker after today's class. That's due on Sunday. And then homework number 10, and I have to decide what we will be doing on that, but that will be due on the 9th. Is there any interest in a final exam review session? All right, we'll have to figure out when we have that, if it's possible to have, so stay tuned on that. Our final exam is not on a Tuesday or a Thursday. It's on the first day of finals. It's on a Friday, and it's from 1 to 3. It will be in this room. So if you've been used to doing something else on Monday, Wednesdays, and Fridays, make sure that you're available for a Friday afternoon at least on the 11th of December. Wow, 10 days from now. Today's the 1st. Now, what we are doing today, MATLAB does in an instant, but we want to get comfortable doing straight line approximations so that we can start doing design or checking what MATLAB is giving us in terms of an output. And these are just approximations, and they're straight line approximations, and they're designed to be performed fairly quickly. That's why it's going to take us 75 minutes to sketch one Bode plot. But we will see. What we are doing with Bode plots is we're really creating 2 sketches, a magnitude plot, and this magnitude plot is of h of j omega, its magnitude, in dB, or it's 20 log the magnitude of that transfer function, h of j omega. And the phase plot, we are just sketching the angle of j omega, and both of those plots are with respect to frequency, and frequency is on a logarithmic scale. So we now have this semi-log plot for the magnitude in dB, and we have a semi-log plot of the phase, or the angle of that transfer function. And then if somebody needs that information, magnitude and angle, at a particular frequency, you can read along the frequency line on both of those plots and find the magnitude and angle. And if you're looking for sinusoidal steady state, then you can quickly fill in those variables in the expression for y sub steady state of t using this. And it also tells us something about the shape of our transfer function, or the type of filtering that particular transfer function might be imposing on our system or on the signals that are being processed by that transfer function. And the techniques that we are developing today are for minimum phase transfer functions. Do you remember what minimum phase means? If I said the system needs to be stable, I hope you remember what that means. What does that mean? Where are your poles? If h of s, if the transfer function h of s is stable, what are we saying about the poles of that transfer function? They're in the left half plane of the complex S-plane. Minimum phase trumps that a little bit, and it now says all of your zeros also have to be in the left half plane. Minimum phase, then, what we're sketching is saying that all of the poles and zeros are in the left half plane. And we actually allow poles and zeros at the origin or on the imaginary axis to make these sketches. We just don't want anything in the right half plane. Those would then be non-minimum phase poles or zeros. Let's then look at this relative to an example. Maybe I should ask, how many of you worked this example over break? You've had a week to do it. You weren't even here to get the assignment, unless you watched the video. So if you watch the video, thank you for watching the video. Then we have the transfer function, which is this 4,000 s plus 0.1 over s plus 200, and then let me say that this one is s plus 6 squared plus 8 squared. If you had to tell me what form that transfer function was written in, how would you describe that form? And here you have two options, really. Is it time constant form or is it pole zero form? This is pole zero form. Which is the form that's ideal for sketching poles and zeros in the complex S-plane. And from this structure, the way I factored it, you should be able to immediately state where those poles and zeros are located, the way that it's written. Let's just do that from the top down. Let's look at the zeros. Do we have any finite zeros? We do have a value of s, a polynomial in the numerator that will cause the whole thing, h of s, to equal 0, and that's when s is equal to minus 0.1. And we will call that a linear zero factor. And the reason we're calling it a linear zero factor is because we have s plus 0.1, and I'm emphasizing the power of that s. The power is 1. That factor is then a linear. It's linear in s because of just raising s to the first power, and it now has a finite root or number that will cause that factor to vanish. What about the poles? And one thing that you can quickly, and this will be on your homework, some of these ideas, it's nice to keep track of how many finite zeros you have, how many finite poles you have, and their difference. And I will call that the pole zero excess. Typically we have more poles than zeros. How many poles do we have? If you counted the x's on your S-plane, how many x's would you count? 4. So now you have a pole zero excess of 4 minus 3. 4 minus 1, the math is too hard for me today. 4 minus 1, or 3, is your pole zero excess. And that's going to be important when we start answering questions in a little bit. But here, where are our poles located? We have one at the origin, one at minus 2,000, and where are the others? What did I say? Did I say 2,000? Minus 200, and the origin, and then where are the other poles? Those are complex, aren't they? They're minus 6 plus and minus j8. So we write those down. We have a pole at the origin, and that's going to have particular behavior in the Bode plot because it doesn't have a constant added to it. It's right at the origin, so we'll distinguish that in our sketches. We have a linear pole factor that gives rise to a pole at minus 200. And then we have this complex factor that has poles at -6 plus and minus j8, and all of these poles and zeros are on the imaginary axis or in the left half plane. So these are the kinds of poles and zeros that we are learning how to sketch in the Bode plot. This is then a quadratic pole factor. Now, you will thank me later, but we are actually going to approximate or change or modify this complex factor so that it's easier to sketch. We said we're trying to do these sketches quickly, meaning let's now figure out how we can approximate these complex poles as basically two real poles. In doing that, it's nice to write these quadratic factors, and this could be either in the numerator or denominator. We can factor it the same. But here we have s plus 6 squared plus 8 squared, and that's factored directly to identify the imaginary part and the real part. But if we multiply that out, we have s squared plus 2 times 6, or 12s, plus 6 squared plus 8 squared. And I would have done the same. That's a 3, 4, 5 triangle, which says that this is actually 10 squared in terms of value. 6 squared is 36, plus 8 squared is 64, and that gives us 100, or 10 squared. We now have this expression, s squared plus 12s plus 100, and you might see this written for a standard factored form as s squared plus 2 zeta omega sub n s plus, and somebody was complaining that I wasn't using enough Greek symbols, so now we get a new one. We get zeta. Or they were commenting, they weren't complaining, they just said you can use some more. Now, these particular variables have specific names associated with those. This omega sub n is actually the natural frequency of that quadratic, or associated with that quadratic factor, and this zeta is our damping factor, which lives between 0 and 1. So this is, let me just say, 1 standard form. And if we compare coefficients between what we actually have in our example, in our numerical example, which is s squared plus 12s plus 100, we can identify what the natural frequency is and what the damping ratio is for that particular quadratic factor. And we can do that by comparing coefficients or terms in those two quadratic expressions. Meaning, if we look at the coefficients of the s to the 0, or the constant term, we find that omega sub n squared is equal to 100, or the natural frequency, omega sub n, is 10 radians per second. And that's actually the distance from those poles to the origin. If you think of where they were -6, +8, and minus j8. Those are now on this right triangle that have sides of 6 and 8. The hypotenuse is 10. That's the distance those are from the origin. So the natural frequency of those complex roots are, essentially, you can get out your ruler and measure how far that way they are from the origin. If they didn't nicely solve as omega sub n squared equal 100, for example. If we look at the other coefficient, we've normalized this polynomial to be monic. That's when this the leading coefficient is 1. So we're assuming that we've factored the quadratic to where the leading coefficient is 1, and then we can identify the two coefficients uniquely. S to the 1 in this case says that we have 12, and don't ask me why I'm putting it in the other direction. Let me do it. So now we have 2 zeta omega sub n equaling 12. Or if we divide out the 2, we see that zeta omega sub n is equal to 6, or our damping factor, or damping ratio, zeta, is now 6 over omega sub n, and we just found omega sub n to be 10, so that's now 0.6. And if we were sketching that in the S-plane, then the pole in the second quadrant would be right there at minus 6 plus j8, and this distance omega sub n is 10. And if we got out our compass, then if we completed that circle, each of those points on the dashed line would be 10 units away from the origin, is what I'm meaning by that red arc. And in this case, sometimes you might have people talking about this particular angle theta. Zeta is the cosine of that angle theta, which in this case is 6 over 10. It's the adjacent side over the hypotenuse for that right triangle. Its real part is 6, the hypotenuse is 10, and we can then solve for theta. If you had your protractor and wanted to sketch that and you didn't have your lines, or just maybe you had your real part identified, now the inverse cosine, do you remember what that is? Or can you eyeball it? If I'd sketched this accurately, you could eyeball that. It's more than 45 degrees. And in fact, it's one of those common angles of 53.13. So if you measured that with the protractor and found 53 degrees, you would say, oh, the zeta is 0.6 associated with those complex factors. What we are going to do in this course to sketch these Bode plots, there's the twin in the third quadrant. We are going to, no matter what value of zeta is, no matter what angle that theta is, whenever we have complex, we're just going to rotate both of those onto the real axis. That's why this natural frequency is so important. We're just going to rotate those and say we have two real poles at s equal minus 10. That's an approximation. It's not going to give us a real accurate Bode plot, but it will give us something to sketch very quickly. Is that clear? We'll talk a little bit more about that in a minute. Which means, really, when we're sketching these Bode plots, we really only need to know how to sketch constants, how to sketch linear factors. The quadratic factors will just be two linear factors, and a pole or zero, or poles or zeros at the origin. That's all we need to sketch. But before we sketch those, we actually need to make sure that this transfer function is no longer in the pole zero form, but it's in time constant form. We need to convert h of s into time constant form. Or what we're really doing is we are normalizing the constant coefficients in all of those linear and quadratic factors to be 1. If we do that in this particular transfer function, we started with 4,000. Then in the numerator, if we pull out the location or the constant associated with the location of that 0, that was 0.1. We now have s over 0.1 plus 1. That's just converting this numerator into time constant form. Just factoring out the 0.1 to give us a constant of 1. We don't have to touch the pole at the origin, but we do have to touch the other two. And the one had a pole at minus 200, so we factor that out. And the other one had a natural frequency squared of 100. We have to factor that out. And what we are going to do is we will write that in such a way that we now have really sort of normalized this S term by the natural frequency of 10. Or what we have done, if we look at the quadratic factor, in the standard form we said we could write it as s squared plus 2 zeta omega sub n s plus omega sub n squared. But now we have factored out the natural frequency squared from all terms, and now we have an s squared over omega sub n squared plus 2 zeta omega sub n s over omega sub n squared plus one. So if we multiplied that in brackets by omega sub n squared, we better get the equation that we started with, and we do. And we can now start to clean this up a little bit so that now we can rewrite that as s over our natural frequency, that quantity squared, plus 2 times the damping ratio times s over omega sub n plus 1. In our numerical example, this ended up being 12 over 10, or 1.2, and that's equal to, or that then says that zeta, which is twice zeta is that says that we're getting back what we should have gotten back or expected to get back, which was a damping ratio of 0.6. And you could say that this is really a normalized standard form. Again, what we are going to do is we will actually just say, oh, we found this. Now to sketch it, we are just going to agree in this class that we will, whatever zeta is, we're just going to force it to equal 1. And that's going to push those complex roots to be on the real axis, because that would then be a pure squared linear factor if zeta is equal to 1. That's the approximation we're making. We're just changing zeta. If this case is it's 0.6, we're just making it 1 in our sketching. Let's now start sketching this. Our strategy is really just two pieces. We will first sketch the individual terms that we've now identified in this time constant form. And then once we've sketched all of those on the same set of magnitude plot and phase plot, we will try to combine those arithmetically or add them up as a function of frequency, point for point. And since these are all straight lines, then we just have to worry about where are those straight lines and how are they sloping to make the addition work. So add all terms together for all frequencies. That's our strategy. Let's now look at the terms that we've now identified. Or these different factors or types of factors in this time constant expression. Do you see in this expression for h of s that we've normalized all of our constants to be 1? And if we combine all of those constants that are out front in the numerator and denominator, we will just get one number, and that's the constant that we can now sketch. Got somebody excited, didn't it? Set off a siren. And that's what you should do when you're plotting these. You should say, oh, this is exciting. Let me now sketch the constant term. Here's the constant factor. But that was a quick response. What was the time constant on that response? It was just one ring, wasn't it? He didn't have to play it very long, did he? All right, constant factor. What's the magnitude? The magnitude, we had a 4,000 to begin with, and we factored out a 0.1 from the linear zero factor. Downstairs, we had a 200 and a 100 that we factored out. And we can clean this up a little bit, maybe. We can say, how many times does 200 go into 4,000? 20. So now we have 2 over 100. Kind of small, but this is now 0.2 or 2 times 10 to the minus 2. And if you forgot your calculator on the final, you still have a prayer, because you can do this in dB. You now are looking at 20 times the log of 0.02. But you realize that that's 20 times the log of 2 times 10 to the minus 2, or 20 times the log of 2 plus the log of 10 to the minus 2. And that minus 2 power on the 10, because these are logarithms, allows us to write that as minus 2 times the log of 10. And you already know what the log of 2 is. Yes? It's approximately 0.3. And you know what the log of 10 is, correct? That's 1. So now we have 20 times 0.3, or 6, and we have minus 40 times the log of 10, but you said the log of 10 was 1, so we have 6 minus 40, or that constant of 0.02 in dB is minus 34 dB. What is 0.1 in dB? Just to check your sanity on this, if you now had 20 log of 0.1, that's 10 to the minus 1, that's minus 20 dB. And 0.01, ten to the minus 2, so it's minus 40 dB. So we're in between minus 20 and minus 40. Yes, so we're in the ballpark. We're at minus 34 dB. If we now sketch that as a function of frequency, and this is really log of omega, now we have 10 to the minus 1, 10 to the minus 10 to the 0, which is 1, 10, 100, etc. And this is now the magnitude of dB of this first term. Let's say those are our minus 20 and minus 40 curves. We are now at minus 34 dB. That's how difficult this is. Do you see why the sirens went off? When you said, oh, I'm sketching this constant's Bode plot. It's just going to be a straight line for all omega, and you just have to locate that straight line. What's the phase curve of this gain look like? The constant factor, did it have a negative sign anywhere? No, it's a positive number, isn't it? So what's the angle of a positive number? Now you're looking at the angle of some number on the real line, on the positive real line, and these angles are all relative to that positive real axis. So this angle is 0 for all frequencies because our gain was positive. That's not even worth sketching. That's just not doing anything to our phase plot. So let's keep going. But we now know that that contribution is nothing. Let's now look at the second factors, which are these linear factors, and let's say that now 2a is the 0 factor. Which we've now factored into s over 0.1 plus 1, and it's upstairs. We are really sketching this for s equal to j omega. We want to know how does this factor contribute to the overall transfer function as we walk up the imaginary axis. And did anyone talk about fairy tales over the break, around the table? Did they say, what are you learning in school? We're learning Goldilocks. I'm paying how much for you to learn fairy tales? Remember Goldilocks, and that's going to help us sketch these curves. But before we get to Goldilocks, let's look at the magnitude. That's now 20 times the log of that term, that term's magnitude. And what did we say about this? We could actually write this out in written terms. We could say that expression we're agreeing is going to be flat or level or at 0 dB until where? Where did we agree that it was just going to be 0? Until what frequency? Until the break frequency. Somebody got it. No one else did, but somebody did. Thank you. So the break frequency is 0.1. Will be 0 dB until then. Then it breaks at that frequency. And then what happens beyond that frequency of 0.1? What happens to that sketch of the zero factor? Now it slopes, but since it's a zero factor, it's upstairs, it's sloping up. We talked last time about pole factors and they were sloping down. Now we have to realize that this is now in the numerator. This now slopes, and it's just a single linear factor. It has with a slope of plus 20 dB per decade. And what's a decade? 10 years. Or in this case, it's what we're calling this factor of 10. Or it gives us our slopes of 20 dB per decade. Or if you wanted to subdivide your frequency axis into smaller pieces, then you might look at octaves, which are these factors of 2. And then you're only going up 6 dB per octave. And those are equivalent. But if we now sketch this, and I just get a little bit loose with my labeling, I'll just say that's omega, but it's really log of omega. And this is now the magnitude of our linear zero factor. Remember, our constant was just a flat line. What are we saying this one looks like? And I'm going to assume that this is now 0 dB. And if I had some guidelines, if this was now 20, 40, 60 dB, hopefully those will help me sketch this magnitude of the zero factor. Where do you begin? And that's why we wrote this really in 3 parts. We say we're flat, we're at 0 dB until we hit the break frequency, which is right there. So we are flat on 0 dB until we reach 0.1. And then we start sloping up at 20 dB because it's a numerator or zero factor. Now we go up to 20 at 1, we go up to another 20 at 10, we go up another 20 at 100, and we just keep going. And that should be a straight line if everything was sketched, and it never stops. It just keeps going, sloping. Yes? No, so the question is a valid question. I said that I get a little bit sloppy with my labeling. This is really log of omega, but a lot of times I just label it as omega. But this is a semi-log, and why are we doing it with the log of omega to begin with? to save trees. So we can fit more frequencies on a narrow piece of paper. And we can now go 7 cycles on a paper width instead of who knows how wide that would be if you went from 0.01 or 0.001 up to 2,000 or 30,000. This now allows us to compact that, and it allows us to sketch these plots as linear straight lines in the approximation. Now we get to do Goldilocks. What's the phase? Are there other questions on this sketch? That's pretty easy, and that's how all of these linear factors are. Individually, these aren't difficult at all to sketch. What's the phase look like? We want to look at 3 frequencies. And I will label these 3 frequencies as omega 1. Don't ask me why I'm labeling this way. Omega 0 and omega 2. I frustrated my first grade teacher or kindergarten teacher. 1, 0, 2, 3. All right, omega sub 1. This is the small number. This is the large number. And this one is just right. That's why it's got the 0. All right, there's Goldilocks. Small, just right, and large. Let's look at those, and once we find the phase at each of those 3 frequencies, we will connect those with straight lines, those points. We look at those 3 frequencies and connect with straight lines. And what do we call omega 1? What is a small frequency? And it's all relative to omega 0, which is omega 0 is really our break frequency. So this is the just right, but this is also our break frequency. What is the small frequency relative to omega naught that we've agreed to? Do you remember? That was a decade below the break frequency, or a factor of 0.1. Or I can change the wording and say the cutoff frequency. For this particular factor, maybe it was not properly selected, but what was the frequency or the break frequency of this 0 factor? It was 0.1. We're saying then we want to know what's the angle of this factor. If we now looked at this factor with omega equal to omega 1, we now have 1 plus j 0.01 divided by 0.1, or 1 plus j 0.1. So now we're going over 1 and we're going up 1/10. What's the angle that we've agreed? That's negligible. We're just assuming that's 0 degrees. So up until this break, or a decade below this break frequency, we're assuming that we can approximate the phase of that factor as 0 degrees. That's what we're assuming. That's the angle of j omega 0.1 plus 1. We're looking at that for these three frequencies. And in this case, right now, we let omega equal omega 1. And omega 1 is a decade below 0.1, which is 10 to the minus 2. What about at omega naught? When omega is equal to omega naught, maybe I should say omega is equal to omega naught, the break frequency was 0.1 radians per second. If omega is 0.1, we now have 1 plus j1. What's the angle of that complex number? That's 45 degrees. And it's a numerator upstairs, so it will be a plus 45 degrees. What about when omega 2, that's now the large, or a decade above the break frequency. In our numerical example, that corresponds to 1. Now if you plug in 1, you have 1 plus j10. Now you walk over 1 and go up 10. What effectively is the angle? You walk 1 and you look way up. How far up can you look? So what's this angle between my arms? 90 degrees. So that's as far as we are going to go for a single linear factor. Now we can sketch the phase of this 0 factor. Log of omega, let's say here's 10 to the minus 3, 10 to the minus 2, 10 to the minus 1, 10 to the 0, 10 to the 1. Where's the break frequency? For this 0 factor. That was right here, wasn't it? So now we go a decade before that, a factor of 10. We go do a decade above that, and we identify 0 degrees. We identify 90 degrees. So let's just, that's supposed to be straight. That's 90 degrees. We are now saying that we go there, and what are we right at the break frequency? Maybe I shouldn't have labeled, I'm going to, touch. Okay, if you missed it, you missed it. But what is at the break frequency? What's the angle or the phase? It's halfway between those other two. It's at 45. So what we're doing is we're connecting this straight line. We're 0 degrees below, a decade below the break. We're at 90 degrees, a decade above the break, and we said let's just connect those straight lines with another straight line, and there is our phase curve for this linear 0 factor. It's basically distributing 90 degrees of phase over a 2-decade span. And those 2 decades are centered at the break frequency. What we were talking about, if we wanted to think of this when I was trying to get you to think about walking over 1 and up 10, or over 1 and up a tenth. Here, let's say, is omega naught. And let's say this is now 0.1 omega naught. Let's say this is omega naught. And now do you see that 10 omega naught is way up here in the S-plane? What we are doing is we're saying, oh, here, that's roughly 0. This angle is 45. This angle, we're agreeing, is 90 degrees. Is that clear where those are coming from? Now let's look at the pole factor. The linear pole factor. We've gone from Goldilocks to Shakespeare, to be. Now you can go home at the other break and talk about Shakespeare and just impress your guests completely. All right? Or if you're taking a dance class, maybe you can start dancing. I just now learned that there's gen eds on dance. I was looking at some students' course history and it said, looking at dance. And I wondered, well, how you spend a semester looking at dance. But it's offered. All right. I don't think it was anyone in this class that I was looking at their course history. We were trying to find tech electives, and I go, what is he taking? Looking at dance. How does that work? I don't know. A lot of gen eds I probably don't know anything about. But this is now what we are trying to sketch. J omega over 200 plus 1. Now, once you've factored that, you should be able to sketch it immediately. All you have to do is draw this axis, label it. Let's say this is now 0, 10, 100, 1,000, 10,000. How am I going to sketch the magnitude of this in dB? What point am I looking for now on and this line right here is 0 dB. What's the first point I probably want to identify if I'm looking at the Bode plot? Maybe we can have a class on that. Oh no, not 15 weeks, one day. How's that? Looking at the Bode plot. Where am I looking now? I'm looking for the break frequency, and where is it? That was a very general question. You can give me a very general answer. 200. Okay, it's at 200. Where do I locate that dot? Log of 200 is how far between 100 and 1,000? What fraction of that distance? Log of 2? Log of 2, 0.3. So it's 30% of the distance between 100 and 1,000. We go over to here and say there's 30% and there's 200. So we're now 0 until that point. That's the 200 point. Question? Looking at Bode plot. So this is log of omega. So now if you take the log of 200, what's it going to be? It's going to be 2.3. So the 2 is giving you this 2, and now you go 30% of the distance between 100 and 1,000. So that's why it's nice to know the log of some of these integers. 2, 4. What's the log of 4 if the log of 2 is 0.3? 4 is 2 squared. So now you pull that 2 out in front and you have 2 times the log of 2. 2 times 0.3 is 0.6. So now you know the log of 4. It's 0.6. So if we knew that we were at 40, we would go over 60% of the distance between 200 and 1,000. Is that, or between 100 and 1,000? Now what do we do? And you can't drop back and punt. That's not allowed. Now what do we do? And I said these are not that difficult. First, which way do you go? Up or down? This is a pole, it's in the basement, you're going down, and how far down are you going, and when, at what frequency will you get there? What's your slope? Minus 20 dB per decade. So now it's important that we do go to 2,000. We go to 2,000. And where are we going to be when we get to 2,000? Now we'll be at minus 20. So if this is minus 20, if this is minus 40, then if we went all the way up to 20,000, we would be 30% of the way between 10 to the 4th and 10 to the 5th. Here we'll be at minus 20, here we'll be at minus 40, and we just connect those, and there is our magnitude plot for this linear factor with a break frequency of 200, and I usually encourage you to, if you can write that small, to label your slope. Questions on that? What about the phase of this linear factor? Where's my break frequency? For this factor. Are you guys still tryptophan down on turkey? Yeah? Okay. Wake up. That's why you shake these things at certain frequencies, right? There's probably a resonant frequency of everyone's body. All right. What's the break frequency? 200. So what's that mean? If it's 200, we are right here for the break frequency. But now we're dealing with phase, and what do we need to worry about with phase? Where are we going to end up in our phase? And this is a pole factor. Minus 90. So if we did this line, if this is now 0 degrees and this is minus 90 degrees, where will we end up, or when did we agree that we will be at minus 90 for that point all the way forward in frequency? A decade beyond 200. So now we go to 2000 and we say any point beyond that we're at minus 90. And where are we beginning the angle? For really small omega we're at 0 degrees, And we've agreed that small means everything below a decade below the break. And then right at the break, we are halfway between, and we should be right here at minus 45 degrees. Since this was our break frequency of 200. Is it clear where that came from?
And we know that 200 is the break frequency, so it's 51 plus.
Yes, so the break frequency is right here. That's why we factored out that if we go up, whoops, if we begin with where we started, which was right here, we know that's our break frequency. And we've now just factored it into time constant form, and now the break frequency is right underneath that linear S. So that's now our break frequency, which we just agreed, whoops, that's the zero factor, but in the pole factor, that's now where we have said, okay, we're going to assume that we're flat until then. In reality, where are we actually at for that linear factor? If we just had that linear factor and that was it, where would we be relative to dB? Would we be above 0 dB, below 0 dB, and how far above or below? The actual curve, if you sketched it in MATLAB, where would it be at the break frequency? That's the half power point, or that's this 0.707, or that's minus 3 dB. So you would actually be a little bit below this point, and you would be at minus 3 dB in the actual curve, the true curve. We're just sketching the approximations. Question? So what makes the angle negative for this plot? Anyone want to answer that? It's downstairs. So if you wanted to look at the angle of h of s, you would need to keep track of the angle due to this zero factor, the angle due to this pole factor, the angle due to this pole at the origin, and this angle due to the complex or the quadratic factor. Since these pole factors are downstairs, the angles associated with those are going to be subtracted to give us the contribution to the phase of h. And that's why they are negative, and that's why we go down. We know that that pole is eventually going to give us 90 degrees, but since it's downstairs, it will end up at minus 90. That said, where will we end up at high frequencies? What's our phase going to be? I'm trying to get into the last chapter before we run out of time. Where would our phase be at high frequencies? And what is high frequency in this example? What's the biggest break frequency, whether that's zero or pole? 200. Okay, let's go a decade beyond that. 2,000. So high frequencies are above 2,000. Above 2,000, what's the phase of this going to be? What's the phase contribution from that zero at 2,000? 90. What's the phase due to that pole at the origin? We haven't talked about it, but it's going to behave just like the linear factor at high frequencies. And for all frequencies, what's its angle? Minus 90. I'll just give you that one. So those two have canceled, haven't they? Then you have another minus 90 due to the linear factor, and how many 90s do you have due to the quadratic? 2. So now you have 3 minus 90s. You should end up with your magnet phase at high frequencies at minus 270 degrees. What's the pole zero excess? How many more poles do you have than zeros? You start with 4 poles, you have 1 0, your pole zero excess is 3. Each of those poles contributes minus 90 at high frequencies. 3 times minus 90, you should be seeing a Bode plot headed off to minus 270. Is that where this is going for high frequencies? The phase? It's at minus, and where did we start? Well, that's what we need to talk about now. The pole at the origin. How did I get on the last chapter? I don't know. Let's go back. So I'm reading ahead, I'm cheating, aren't I? I didn't think you could do that until I got out of school. I thought you had to always read linearly through a book. Not. Okay, so you can skip ahead and get... Now we have 3. Let's look at the factor at the origin. And really all we are looking at now, if you were looking at the S-plane, we now have a pole right there, and we are walking up this imaginary axis and finding the distance from that point and finding the phase from that point. Now that it's a pole, the S is going to become just j omega. What's the magnitude of this? It's 20 times the log of the absolute value of j omega. Or this is 20 times the log. The j has a value of 1, or a magnitude of 1, so it's 20 log of omega. And we don't have any other piece, do we? So we're really not doing anything over here. This is a missing piece. Now, if we're sketching this, and what I should have done is this is actually, since it's a pole factor, this is minus 1, so this is minus 20 log of omega, since it's downstairs. No wonder sirens were going off earlier. If you're listening to this, I apologize. You're wondering sirens, Goldilocks, Shakespeare, break. Who knows what we're going to end up with. But this is always sloping. It's not flat. It's always sloping. So this one never breaks. We have a pole at the origin. It's always sloping at minus 20 dB per decade. It never breaks. It's never starting at 0 dB. It's always sloping. So at low frequencies, it has a really big magnitude. At high frequencies, it's very small. We have to figure out, if you were at a birthday party, did you ever play Pin the Tail on the Donkey? Now we have this sloping line. We have to pin it somewhere on the Bode plot. We were looking at the Bode plot. Now we have to figure out where to pin it, this slope. So that's what we need to worry about. If it's always sloping and we know the value of that slope, it's minus 20 dB per decade. Have to keep a straight face. So now where do we locate this sloping line? Can you find a convenient value of omega that would tell you the value of that dB number relative to a particular omega? You could really pick any omega you wanted, and that will give you the magnitude. But if you pick omega equal to 1, log of 1 is 0. So now you know you're going through 0 dB, where? At omega equal to 1. That's our convenient value. Now you know exactly where to pin that sloping line, right at 0 dB and omega equal to 1. Our convenient point is omega equal to 1, which says now we are at 20 log of 1, which is 0 dB. Whoops. Let me erase this curly bracket and put it over here. Got worse. So, what do we have? This pole at the origin slopes at minus 20 dB per decade. Always, it never breaks, and passes through zero dB at this convenient frequency of 1 radian per second. Which says then that if you're sketching this magnitude for a pole at the origin, now we've said here is our convenient value, that's 0 dB. A decade above that, where are we going to be? At minus 20, aren't we? A decade before that, where are we going to be? If it's always sloping, this one will be at plus 20. If we go to 100, where will we be? Minus 40, so that we now are doing this. Ugh. There's our dot right there. Ugh. Is that clear? So this is now sloping at minus 20 dB per decade, and it's passing 0 dB at omega equal 1. What's the phase of this? If we look at this, and I say, okay, what's the angle from here to there? What's the angle from here to there? What's the angle from there to there? I'm just varying frequency. But what are those angles? I'm going from here to there, here to there, here to there. 90 degrees. It's always 90, and it's downstairs, so it's minus 90. So this phase couldn't be easier to sketch. Here is our log of omega, and here is minus 90 degrees. Here's 0 degrees. Here's 10 to the 0, 10 to the 1. It's not rippling, it's actually flat at minus 90 degrees. And we can see that because we now are looking at sketching the phase of this. And what's that? That's a ratio, so we now have the angle of our numerator minus the angle of our denominator. What's the angle of 1? I look at 1 and it's on the real line, and what's my head doing in terms of turning with the angle? And I can't look at the class now. I have to continue to look in the positive real line direction. What's the angle? 0. What's the angle of J? And I'm subtracting that because it was downstairs. So do you see where that minus 90 is coming for all frequencies? What if I had 2 poles at the origin? what would my angle be? It'd be 2 of those minus 90s. It'd be minus 180 for all frequencies. And what would my magnitude plot look like if I had 2 poles at the origin? Where would I pin it? Same place, 0 dB at omega equal to 1, and what would the slope be? Minus 40. Are we getting this? Now, I'm going to finish this up on my own time and maybe provide you with some additional lectures on Bode plots, but the complex factor, what are we going to do? So give me the rest of the class and I'll tell you what we're doing with the complex factor. Anytime you have this complex factor, what are we interested in? We are interested in this natural frequency, which is the distance that pole or those poles are from the origin. We are going to replace those with 2 poles right there. They're on top of each other, this same distance, omega sub n away. And you know how to sketch 2 real poles. That's what we're doing to simplify. And now at the end, you add all of these pieces and parts together, and what do you end up with? This. A straight line approximation of this behavior. You add your constant, your pole at the origin, your 0, your pole factors, you get that magnitude and angle plot, and we'll pick up somewhere on Thursday.